Okay. So first, I would like to thank the organizers for the invitation. It's a real pleasure to come back here. And so my talk will be, so the aim of my talk will be to consider one particular case of what has come to be called the relative local Langlands correspondence, and try to say as much as we can on this particular situation. Okay. So let me first set up the notation. So E over F would be a quadratic extension of periodic fields. I will denote by sigma the non-trivial element in the Galois group. We'll fix V to be an Hermitian space over E of dimension, say, n. And I will consider the two following groups. So H will be the unitary group of V, and G will just be GL and E. And through the choice of a basis of V, you have an embedding of H into G. Okay. And the goal of this talk is to consider, so to study the spectrum in some broad sense of the corresponding symmetric space G over H. Okay. And as explained by Yanis in his talk, this question can take essentially two forms. So either you can look at irreducible representations pi, admitting a model in a space of function on G mod H. So let's say that pi embeds in the space of all smooth function on G mod H. So these are usually called distinguished representations. Or we can look at the problem from another perspective by trying to spectrally decompose, looking for the spectral decomposition of the corresponding L2 space. And I will have to say something on both of these problems, but let me just mention that a lot of work has been already done on this particular case by a lot of people, so mainly Jacquet, and then Fagan, Lapid, and Offen. And as you will see, my talk will mainly be, I will have to revisit their work and give a slight improvement on their main results. Okay, so I will start with the first problem, the problem of determining the distinguished representations in this case. And for this, we have the following old conjecture of Jacquet, which says that if pi is distinguished, then it is self-conjugate, so it is isomorphic to its twist by sigma. And moreover, we have also a kind of converse, so more precisely, the converse holds if H is quasi-split. Okay, so, but let me say right away that this conjecture has been essentially proved. So more precisely, Fagan, Lapid, and Offen. And I will from now on abbreviate their names by FLO because they will come very often in this talk. They have proved the first part of this conjecture in full generality, and also the second part, which is the converse, but only for generic or unitary representations. Okay, so for the question of, just the question of distinction, it seems that we almost have a definitive answer. And so what else can we say? about the first problem, where there is a refinement of this question, which is to look at the multiplicities. Okay, so what about, so by multiplicities I mean in how many ways can pi embeds in this space? So we look at the dimension of the space of entertaining operators between pi and this one. So what about multiplicities? And we denote this multiplicities by m of pi, and by definition this is the dimension of, so either the space of G equivariant map from pi to this space, but by Frobenius reciprocity this is the same as the space of H invariant linear forms on pi. Okay. And maybe an important remark here is that this is not equivalent to just the problem of distinction, because here is a case where you don't have multiplicity 1. So the multiplicity is not just always 0 or 1. And more precisely, the multiplicity can be as high as 2 to the power n minus 1 for a certain principal series. So this is not equivalent to the previous problem. But on this question also, Frege, Lapin, and Orffen have some result, and I will now state this. So let me introduce one more piece of notation. So G prime will be now GLN over F. And so by the work of Arthur and Clausel, we have a base change map from the set of all irreducible smooth representations of G prime and the set of all irreducible smooth representation of G, up to isomorphism, of course. So this is Arthur-Clausel base change. And it turns out that this base change is, as you will see, is telling you almost everything you want to know about these multiplicities. So we can, one important point here is that we can equip these two sets with structures. So they have natural structures of algebraic varieties, we'll see. And so this uses just the Langlands classification. Okay. And for these structures of algebraic varieties, it turns out that this map is a finite morphism. And therefore, you can define the degree of an element, let's say, in the target. So your map degree of base change, which associates to any element in the target non-negative integer. Okay, and to be completely precise, this is defined, so the degree of pi is defined to be the sum, usually the degree is defined on the source, and it's the sum of elements in the fibers of pi, or base change, of the degree base change at sigma. Finite. It's finite. Okay, and these degrees will almost always be just 1 when base change is unramified at sigma. And so in this case, you see that the degree of the base change at pi will just be the cardinality of the fiber. But in general, so this degree is locally constant function on the image of the base change. And as I said, for an element in general position, pi in this image, the degree just cardinality of the pi. So let me give you an example which will be the only actually the only example we'll be interested in this talk, which is the case of generic representations. So let pi be in the image of base change, or I should have said, it's maybe a remark here, is that by Arthur and Clausel, we know that pi is in the image of base change. It's really easy to check. It just means the same there, that pi is self-conjugate. So here you see a direct relation between this base change map and the original conjecture of Raphaël. Okay, so for pi in the image of base change, which is generic, well, so you know by work of Bernstein and Zelevinsky, every generic representation of GLNE can be written as parabolic induction of a bunch of essentially square integrable representations, delta I. And so assuming that pi is in the image of base change, in this case, the degree of the base change at pi is, it's always a power of 2, is 2 to the number of indexes I, such that delta I is self-conjugate. Okay, so it's very easy to compute in practice, whereas the degree is equal to the cardinality of the fiber of the base change. So in other words, base change is unramified as at pi, if and only if the Galois stable, so the self-conjugate delta I are distinct. So it's an easy exercise. Okay, and so now using this degree, I can state another result of Fagan, Lapid, and Hoffman. And basically this results, what this result tells is that you can compute exactly the multiplicities when the base change is unramified at pi, and when it is ramified, you only have one inequality. So for pi, a generic reducible representation, so in general, you only have a lower bound for the multiplicity. And basically, you will have to divide the degree by 2 because we're in the PD case and there are 2 unitary groups of the same rank. I mean, 2 Hermitian spaces, 2 pure inner forms. And okay, it's always a power of 2, but it can be 1, so we have to decide how to divide this in 2. So it's bigger than the upper integral part of half degree if H is quasi-split, and the lower integral part if H is not quasi-split. Okay, so this is what they prove for a general representation, but as I said, so they also prove that equality holds when the ramification, so the degree is just the cardinality of the fiber. In this case, they can prove the multiplicity is exactly this. Okay. Then they conjecture, and also Assad, in a more general setting of Galois pairs, they have conjecture that equality always holds. Actually, it's not just an inequality, it's always an equality for generic irreducible representations. Okay, and this leads to the first theorem. This talk, so theorem A. So this is true. In other words, for generic pi, m of pi is exactly this. So half the degree, essentially, Depending, so we take the upper or lower integral part depending on whether H is quasi-split or not. Okay, and now, so this concerns the first problem, and now I would like to state a result concerning the second problem, so the L2 decomposition. This is theorem A. This leads me to my second part, which Plancherel position. So now we are considering the L2 space of G mod H, and this was considered by Sakellarides and Venkatesh in a far more general setting, and well, so in the setting of general spherical varieties, and actually Sakellarides and Venkatesh have made very general conjectures. That should apply so for spherical varieties. Should apply to almost all spherical varieties. And so using a dual picture, and in the particular case we are considering, this is again, their conjecture is again related to the base change map. So here, again, related to BC. Okay, and I will state the theorem, so which is basically their conjecture in this case. But for this, I just need to introduce another piece of notation here. It turns out to be very convenient to consider not just one unitary group at the same time. So we let H prime be unitary group of V prime, sitting inside G, where V prime is of the same dimension as V, but this is the other, it represents the other isomorphism class of Hermitian space of dimension n over E. Okay, so now we have two unitary subgroups of G, and I can state main theorem in a slightly imprecise form. So there exists an isomorphism of unitary G representations between L2 of G mod H plus L2 of G mod H prime with a direct integral indexed by temp of G prime. So temp of G prime denotes the tempered dual of G prime of the base change sigma times measure. And this measure is the Plancherel measure for G prime. So it's the Plancherel measure for the group G prime. Okay, so this, as I say, this is a quite imprecise theorem because this is a remark I want to make. So first of all, this is not, strictly speaking, a Plancherel decomposition. Also, you can work out from this a Plancherel decomposition. Why is this? Because in the Plancherel decomposition, you just you put together every irreducible. It's a decomposition in terms of isotypic components, basically. But here you can have the same irreducible representation appearing at two different places, namely because the base change is not injective. Okay. And since it is not injective, so this is why I need to consider H and H prime at the same time, because somehow these two representations will be mixed in this decomposition. We will not have a similar decomposition. I mean, for each of the pieces. But one consequence of this is that this is not unique, as stated. There are infinitely many different ways to break sum of twice the same representation of direct sum of two reducible representations. But okay, at the end of this talk, I will try to state a more precise form of this decomposition and relate it also to the factorization of global unitary periods, and this relation will characterize uniquely this isomorphism if it exists. Okay, so I stated the two main theorems of this talk, and now I would like to explain at least part of the proof of theorem A, and then a refined version of theorem B. And for this, I have to revisit the work of Fagan, Lapid, and Offen, and explain how they prove such an inequality. And actually, they prove such inequality basically by constructing explicitly elements, H invariant linear forms on pi. So we'll see how this works. Okay, so I call this the Fagan-Lapid-Offen functionals. And the construction of these functionals is not in a direct way. So it's through a certain transfer of functions that was first proposed by Jacquet and its student Tieng Boyer. So I will not first need to review this. Via Jacquet transfer. And I again need to introduce more pieces of notation. So N prime will be the standard maximal unipotent subgroup of G prime. So a group of upper triangular unipotent matrices. And the same for G, I will denote by N standard maximal unipotent subgroup. And we have to fix generic characters on these two. So let's say psi n prime for n prime and psi n for n. So these are just generic characters. Okay, and what Jacquet and Ye has proposed is the transfer of function between G and G prime for a certain, so with a view towards a comparison of relative trace formulas for the double cossets of G prime by N prime on both sides and double cossets of G by H on the left and N on the right. So as usual, this goes to the notion of orbital integral. So we have associated relative orbital integrals here. So for example, for test function f on G, you can define for a certain set of regular elements in G, so gamma. This is regular, it should be taken in the relative sense. So it means that, okay, we'll say that, okay, after. So we associate to gamma the relative orbital integral of f at gamma. This is just you integrate over h times n. So h on the left and n on the right against the character psi n. Okay? And here regular means that the stabilizer is trivial. And the same for G prime, but now with the action of n prime times n prime. Okay. So we have these relative orbital integrals, and so Jacquet and Ye, they propose to compare them, and for this you need, as usual, a matching of orbits. So this takes the form of an embedding, a natural embedding between the double cossets, regular double cossets in G, let's say, inside the regular double cossets in G prime. And then using this matching of orbits, you have a notion of matching of functions. So we'll say that f test function on G match the test function on G prime if the orbital integrals are the same for matching orbits. So for regular orbit, which by this matching of orbits is sent to a regular orbit delta. So, but this is not quite true. You need to introduce some transfer factor. These are just transfer factors. So we should have this equality, and also the relative orbital integrals of f prime should vanish on every element which is not in the image. So this is a very quick reminder on this transfer. So you have a notion of transfer, and the basic theorem in this case, due to Jacquet, is very important, which is that every function f match a function f prime. And you have a kind of converse, but I don't want to state it. You have a kind of converse if you consider h and also h prime at the same time. Okay, but this is all I want to say about this transfer. And now I will explain how this is used by Fagan, Lapid, and Offen to construct this function also. The definition goes as follows. So let me say that by comparison of global relative trace formulas, so more precisely, they use a Kuznetsov trace formula for G prime and what is called the Jacquet trace formula for G. Fagan, Lapid, and Offen, they have proved. So they have defined for every tempered representation of G prime, reducible one, the H invariant linear form. So alpha sigma H, not quite on the base change of sigma, but rather on its Whittaker model. Moreover, it is characterized in some way. So how is it characterized? So it's characterized by a certain identity between relative characters. So let me write it like this. So GH base change of sigma will be the relative character on the G side, and this should match relative character on the G prime side, or matching functions f and f prime. And let me define you these functionals. So by definition, these are sums over orthonormal basis of the Whittaker models. So I'm assuming over some orthonormal basis of alpha sigma h. So this is the right action of f on the Whittaker function w times w1 bar. and this one. Some similarly over an orthonormal basis of the Whittaker model, f prime acting on the right and w prime 1. So you can easily check that these functionals have the right equivariance properties. And this one is usually called a Bessel distribution. And this one, a relative Bessel distribution. It's not hard to see that this kind of identity characterizes uniquely the linear form. Okay, so now I would like to use this to explain sketch a proof of theorem A. Or maybe a good remark there is that so this is how basically how Fagon, Lapin, and Offen proved their inequality, because they constructed a certain number of functionals, and for generic pi, I mean general pi in general position, they can count how many of them they constructed, what is the dimension of the linear span of them, and they found exactly the degree of the Billig change. And then they used some fact that the multiplicity is upper semi-continuous to deduce the result everywhere. Okay, and so the proof of theorem A, remember theorem A is something which will apply to every generic reducible representation, but I will reduce, I mean, only consider the case of tempered representation, but this is the main case, because you can easily reduce to this one using some Macquet machinery. And it will be convenient also in the proof to consider H prime at the same time as H. So I will define M prime to be the multiplicity for H prime. Okay. And we already know an inequality for M of pi and M prime of pi. So if we want to show that these inequalities are actually equalities, we just need to show the reverse inequality just for the sum. So by Fagon, Lapin, and Offen inequality, we just need to show that M pi plus M prime of pi. So Fagon, Lapin, and Offen are telling you this is at least the degree of the base change, because I sum over the two uniforms, but just need to show that it is at most the degree. Okay. And we'll use these functionals of Fagon, Lapin, and Offen, but we'll use them through these relative Bessel distributions. So we have to reformulate the definition of the multiplicities in terms of such functionals. And this is very easy. So let me set X to be G mod H, disjoint union G mod H prime. Okay. In order to consider the two unitary groups at the same time, then M of pi plus M prime of pi is also the dimension of certain space of n equivariant functionals on X, the psi n equivariant functionals, which moreover factorize through the maximal pi isotypic quotient. So this is not hard. This just uses Frobenius of reciprocity plus the existence of and uniqueness of Whittaker functionals for pi. Okay. But now I will denote also, so for sigma, the tempered representation of G prime, we have the relative Bessel distribution GH sigma and GH sigma prime sigma that both belong to some space of functionals. So by their very definitions, they are invariant respectively by H and H prime on the left. So these are functionals on this space, X. But moreover, there are n psi n equivalent on the right, and so these are n psi n equivalent linear forms. Okay, and I will denote by G sigma the sum. Okay, so the key lemma is this one. Is that, so this space we are interested in is included in, so this can be, this is a space of abstract functionals, and this can be recovered from these explicit ones. So in precise terms, I take the span of this for sigma which base change to what I will denote by omega pi t, so where omega pi t in the temper dual of G is the connected component pi. So this set has a natural topology. You can consider the connected component containing pi and just look at representation whose base change lies in this connected component. And this is not quite true as written. You need to take the closure. And this is, so we are considering spaces of linear forms, and this is the closure for the weak star topology. So what it is saying in concrete terms is that if you have a functional here, and a function which vanish on all of this, then it should vanish on this function. Okay. So let me sketch quickly the proof of this lemma. So the point is to use a local Kuznetsov trace formula. And the local Kuznetsov trace formula, so this is something living on G prime. It says something, it is an equality between an integral over orbits, so of the product of two orbital integrals with an integral over the temper dual of a product of two Bessel distributions with respect to the Plancherel model. Okay? And of course, f1 prime and f2 prime are test functions on G prime, but what I want is something on X. And Jacquet transfer can be refined. I mean, as I said, you consider the transfer for H and H prime. And then this gives you a transfer between G prime and X. Okay? So if Fk prime match a function phi k on X for k1 or 2, then you can rewrite both the left and the right hand side as something living over G. So here this is by definition of transfer. You can rewrite this basically because these orbital integrals are essentially the same up to transfer factor, but it disappears when you take the product. And on the right hand side, so this comes from there actually. This comes just from the definition and the characterization of the relative Bessel distribution on G. So you get G sigma. And therefore, these two sides are equal. And here you see a link between this concrete relative Bessel distributions and these orbital integrals. And then you use some localization principle of Bernstein and Zelivinsky, which can be used to show that these are dense in the space of all functionals. And you deduce that the G sigma for all sigma is dense in the space of all n psi n equivalent function on X. So this is almost what you want, but you want a restriction on sigma here. An obvious way to do it is to project to the Bernstein component of pi. You can do this. It's Bernstein center is acting on CC infinity of x. But this is not quite enough because this connected component of pi might be much smaller than just the intersection of the Bernstein component with the tempered rule. So you can think of the Steinberg, for example. So I would just say it orally. There is a way to project directly over the connected component of pi from there, using some a priori estimates on this space of functionals, showing that they extend to some Harish-Chandra-Schwarz space where there is a way to project directly to such connected components. And then the lemma is proven. Okay, so now I explain the end of the proof. Okay. So I will draw square. So we let B G prime and BG will be the spectra of the Bernstein centers of G and G prime respectively. You have the space of irreducible representations of G and G prime, and you have the base change map between these two. And it turns out there is a similar base change map at the bottom, which is compatible with the natural projections, which you may call infinitesimal characters projections, or lambda. Yes. Okay. And okay, we'll use this lemma because this lemma will tell you that value of a functional here is uniquely determined by value of this functional on a particular test function, right? So we need to describe what kind of, once you fix a test function, you get a function on sigma, yeah? And we need to know what kind of function you get. And so this follows from theory of Jacquet functionals. So these are explicitly defined Whittaker functionals. And this is on the G prime side. The set of functions of this form, f prime is a test function on G prime. This is precisely the Bernstein center of G prime, so regular functions on BG prime. But by definition of the relative Bessel distributions, this is the same at the space of functions. Sigma gives G sigma of f for f at this function on x. Okay. So you know what this space of function looks like. And now, so you have pi here. You have the connected component of pi, the full one, denoted by omega pi prime. Here, the inverse image. And by omega prime pi lambda, this is the image. It's important of omega pi prime and omega pi lambda, the image of omega pi in this Bernstein varieties. Okay. And basically, what it is saying, this key lemma, is that functional for pi in this space here only depends on this function for sigma in omega pi prime. And this equality tells you this is precisely the space of regular functions on this, the image of omega pi prime in BG prime. So every element of this factorizes through a quotient like this. Regular functions on omega pi prime lambda. But now it factorizes through a further quotient of this because of the theory of the Bernstein center. This is trivial on the maximal ideal of lambda pi here. Okay, and now the point, so, is that because this is factorized through the pi maximal isotypic quotient, right? And the point is that this space is of dimension precisely the degree. Okay, and the reason is that this is because here lambda here restricted to omega pi and omega prime prime. These are isomorphism near lambda pi and its inverse image there, so that you can compute either the degree there or there, it's the same. And here this is kind of the naive way of defining the degree, but this is the good, I mean, this is the same as the true degree because this base change is flat over its image. Okay, so this ends the discussion of the proof of theorem A. And now I just want, in the last 5 minutes, to state a refined version of theorem B, which was the Plancherel decomposition, and make a link with the factorization of global unitary periods. So it will again be in terms of these functionals defined by Fagan, Lapin, and Orphan. And the result will again be a consequence of their work. This is the last part. So recall that theorem B was telling you that you have a decomposition of L2 of G mod H plus L2 of G mod H prime as a certain direct integral of the base change of the tempered representations of G prime. Okay, so now we start from a tempered representation of G prime, and I define a certain G invariant semi-definite scalar product, not like this. This is G invariant semi-finite scalar product. And this is defined the following way. So X, remember X is G mod H. I'm considering H and H prime at the same time, so this is a complete representation. So you sum over the Whittaker model, orthonormal basis for the natural scalar product on the Whittaker model of the base change of sigma of, let's see, alpha sigma H and alpha sigma H prime were my notations for the functional defined by Fagan, Lapin, and Orphan, but I will denote by alpha sigma the sum. So again, the action by right translation of phi 1. So let me just explain the notation here. So if phi is a function on test function on X, which decomposes as a sum of something on G mod H and something on G mod H prime, then alpha sigma of phi acting on W is alpha sigma H, phi H, right action of phi H on W, plus the same thing for H prime. Okay, and the important remark is that, so this is a G invariant semi-finite scalar product, and you can take the completion. Complete. And this gives you something which is isomorphic. So this is the G unitary representation, and this is isomorphic to base change of sigma. Or more precisely, also its completion for G invariant scalar product. Okay. And theorem B prime, which is the last refinement of theorem B, is that so this is the Bernstein way of describing a Plancherel decomposition. for every test function phi1 and phi2 on X, test functions, the L2 scalar product of phi1 and phi2 decomposes so L2 as an integral over the tempered dual of G prime of these scalar products. For the Plancherel measure again on G prime. Okay, so and the remark is that this precise formula easily implies the theorem B, just by taking some completion. May I take just 5 minutes to state? So, okay, I will not explain the proof of this, but what I would like to do now is just to make the link with the factorization of unitary periods. And there also the most definitive results were obtained by Fagan, Lapin, and Offen, and what I will just do now is restating their main results. So I changed the setting now, will be in a global setting, so K prime over K is a quadratic extension of normal fields. Okay. And okay, the situation is the same as before. H embeds, so H is a unitary group, and you embed it into GLN of K prime through the choice of a basis. Okay, and what you want to look by Caspidal automorphic representation of G, and you are interested in the period along the subgroup H, which, let me recall, is just the linear form on pi, which ends the Casp form to its integral over H. Integral is absolutely convergent. And okay, actually to make the link with the Plancherel decomposition, it's easier to look at the dual object of this period. And this already appeared in Yannis' talk, so the dual object. This is a map from, so we take G of the Adels mod H of the Adels, test function compactly supported smooth test function there, and you go from there to pi. How do you do this? So if you start from, I call it 5. Test function there, you can first construct a natural function on the automorphic quotient of G by just summing over the rational points. So this is defined this way, where the dot represents the variable. And so this is in C infinity of the automorphic quotient of G, and for there you go to pi by projection. Okay, so this is. So Yannis explained in his talk that basically what the relative trace formula is about spectrally decomposing the L2 inner product of two such functions. Of course, this needs to be regularized, but if you only look at the P part, this already converges very well, and this is the dual object of the period, or rather the square of the period. Okay, and to state the result nicely, I again need to consider certain pure inner forms. So, but here you have far more pure inner forms. You just have two Hermitian spaces. Isomorphism classes of Hermitian spaces of dimension n, you have infinitely many. So how do you define? It's better to replace this quotient by this one. So I call it X of A. So where the quotient here is taken in the category of algebraic groups, I mean it's an algebraic quotient, and then you take the points. And this can be described as an infinite disjoint union of quotient like this, where you vary the unitary group. And for this space, you can define exactly the same way such a map. Okay, and now I will state the main theorem. So this is due to Fagan, Lapin, and Offen, and also Jacquet when n equals 3. The method is due to Jacquet. So let's find a factorizable test function on X of the Adels. Then sigma phi pi is 0 unless pi is the base change, but this time this is the automorphic base change. So sigma is a cuspidal automorphic representation of GLN K. And if this is a base change, you have a formula for the 2 norm of this sigma phi. So 2 over n in terms of L functions. So you see adjoint L functions, so these are partial L functions for a certain sufficiently large set of places S times, so this is the adjoint L function, and this is the adjoint L function twisted by the quadratic character corresponding to our extension. And you have a product of the places in S, so the ramified places, of so I take sigma to be a cuspidal automorphic representation with base change is pi, and I can define now locally almost everywhere. Also, we only did it for periodic non-split places. You have a scalar product here. Okay, but you can define the same for the Archimedean or split places. It's easier for split places. Plus the same thing for sigma twisted by eta. Right? So where this is the quadratic character associated with this extension. Okay, so this is just our statement of the main results, but the point is that this fits very well with general speculations of Sakellarides and Venkatesh on the factorization of global spherical periods and linking in particular these global factorizations to the local Plancherel decompositions. And one important remark maybe here is that the fiber of the global base change of a pi is now just consisting sigma and sigma tensors. Sorry for going over time, we stop here.